Hello, this is Mrs. Pinkerton, and 2.6 covers resonance structures and formal charge. Sometimes when we draw Lewis structures, as we did in 2.5, there's more than one valid structure that you could draw based off of the rules. So we use formal charge to determine which structure is the better Lewis structure. So formal charge is the hypothetical charge the atom would have if all the atoms had the same electronegativity. It can be used to identify the most valid Lewis structure. So again, this is if you can draw more than one Lewis structure based on those rules. We're trying to find which one is the better structure. The best Lewis structure will have most of the atoms with a formal charge of 0. Negative formal charges are assigned on the most electronegative atom. So for example, fluorine is the most electronegative atom. You should have a negative charge on there if it's not 0. And the sum of the formal charge on each atom must add up to the overall charge of the formula. So if you have a plus or minus charge on your molecule, it has to add up to that. The equation some people use to get the formal charge is you take the valence electrons on your atom and you minus the half the shared electrons plus the unshared electrons. You can do it that way. Sometimes I just count the valence electrons and I minus the electrons that are connected to my atom. So I'll show you both ways. So let's calculate the formal charge on these three atoms here. So the first, we have two possible structures of carbon dioxide, and we're going to determine which one is the valid structure. And again, we're looking for a formal charge of 0 on all the atoms, or if we don't have a 0, then we're looking for the negative, if we come up with a negative, to be on the most electronegative atom. So let's do the first one. So here we have oxygen, and oxygen has 6 valence electrons. So if we look up here, 1, 2, 3, 4, 5, 6, 7, 8. So oxygen has 6. So we have 6, the valence electrons on oxygen is 6. I'm going to use this equation minus half the shared electrons. So there's 2, 4. There's 1/2 of 4, right? Plus the unshared electrons, which are our lone pairs, there's 2 and 4. So that is 4. So the formal charge on oxygen, so this is 2, would be 6 minus 6. So this would have 0, right? The other way I do it, instead of this half is 4, I just take 6 valence electrons and then I count 1, 2, and then I just already half this, 3, 4, 5, 6. So there's 6 there. And that makes it easier than having to do this equation, but it's up to you. So carbon has, if we look up here, carbon has 4 valence electrons, and you'll know that by heart. We use carbon a lot. So we have 4 minus half the shared electrons, which is 2, 4, 6, 8, right? So 1/2 of 8 is 4. And then plus the unpaired electrons is 0. So the formal charge on carbon is also 0. And finally, this oxygen is the same as the other, so that's going to be 0. So each of these has a formal charge, if I'm going to write it in a different color, of 0, 0, 0. Okay? So already that already looks like it's probably the best structure because it's 0 on each atom. But let's do the other ones. So this oxygen, again, has 6 valence electrons normally. Then we minus how many electrons it has attached to it, basically, is what I do. I do 1, 2, And then there's half of these, 3, 4, 5. So 6 minus 5 gives me 1. So that has a formal charge of +1. It's positive. And this carbon normally has 4. And then I have 1, 2, 3, 4 attached to it. And that's 0. And oxygen usually has 6 valence electrons. And then it has 2, 4, 6, and then half of the shared one is 1, so that's 7. So 6 minus 7 gives me a -1. So I have a +1 and a -1. That's not good. So this wouldn't really be a valid resonance structure compared to the one we just did. And finally, let's do the formal charge on this one. Again, oxygen has 6 valence electrons. We just did it on this side here. It's the same thing. So 6 minus 7, oops, gives me a -1. This carbon has 4 valence electrons, and I've got 1, 2, 3, 4, or half of 8, which is equal to 0. And then again, this oxygen has 6 minus 1, 2, 3, or half of 6, which is 3, plus 2 is 5. 6 minus 5 gives me 1, a +1. So it's just it's the same as the other one, it's just flipped, right? So again, that's not the best structure. Okay, let's try the next one. You can pause it. So your turn, figure out the formal charge on each, and see if you figure out which one's the best structure. Okay, so sulfur. We have sulfur, we have nitrogen, and we have carbon. So we know that sulfur, nitrogen, and carbon are our elements. I need to go to the periodic table. I see that sulfur has 6, nitrogen has 5, and carbon has 4 valence electrons. So you need to know that first. 6, 5, and 4 valence electrons. So sulfur has 6 minus, I have 2, 4, 6, and then this is half of that, 7. 6 minus 7 gives me a -1. This carbon has 4 minus 2, 4, 6, 8, half of 8, 4 minus 4, which is 0. And then nitrogen has 5, so then I have 2, 3, 4, 5, or half of 6, which is 3, so 5 minus 5 is 0. So that's the first one. Sulfur here, again, 6 minus 2, 4, 5, 6. 6 minus 6 gives me 0. Carbon again is 4 minus 4, which gives me 0. And nitrogen is 5 minus 2, 4. And then I have 5, 6, or half of 4, which is 2, but 6. And that's -1. So I have 0, 0, -1 on this one. So let me make those red so I just know which one's my formal charge. And I have -1, 0, 0. And then my final one is 6 minus 2, 3, 4, 5, which gives me +1. Carbon again is 4 minus 1, 2, 3, 4. 4 minus 4, which gives me 0. And then nitrogen has 5 minus 2, 4, and then half of that is 1, 2, 4, 5, which is 0. Okay, so let's look at these and see which one's the best. First, we see here that the sum of the formal charge must add up to the overall charge of the formula. So the sum of this one here, 0, 0, plus 1, does not add up to a negative charge, and this has a negative charge on it. So this is not a valid resonance structure. Both of these other two do add up to -1. So now here we have a negative on the sulfur, and here we have a negative on the nitrogen. So we need to determine where the negative should be. And again, the negative formal charge must be on the most electronegative atom. So if I go to my periodic table and look at sulfur or nitrogen, we'll see that if we look at our periodic trends, we'll see that nitrogen is more electronegative. Remember, it increases as you go across and as you go up, and they're pretty close together, but nitrogen actually is the more electronegative atom. So the correct choice would be the middle here. So again, make sure you're remembering from your previous units, you know, periodic trends, Coulomb's law, all that stuff comes into play, and everything in chemistry builds on itself. Now we're going to talk about resonance structures. Sometimes when drawing a Lewis structure, you might find that there is more than one arrangement of bond electrons that are equally valid. These are called resonance structures. So when we were drawing our Lewis structures, remember we could take the extra electrons from one or more of the oxygens. We call those resonance structures. Double arrows are drawn between the structures, indicating that the actual structure is an average of the resonance structures. And resonance structures are present simultaneously, so they don't flip between them, meaning that even though we draw it like this, that doesn't mean that there's a double bond here and then there's a double bond there. There's actually this like hybrid bond. It's a little bit shorter than a single bond, but longer than a double bond because it's shared between the two bonds, okay? So a lot of times students will say that there's a double bond here and then it flips and it like moves around, but it doesn't really move around. You want to think of it as being more shared between the two bonds. So these electrons can be described as delocalized, and they're represented with these dashed lines. So these dashed lines right here. And the bond strengths are an average length. Again, this would be like 2, this would be a bond length of 1. So if you've got 2 resonance structures, how do you calculate the bond order or the bond length? So how you do that is you take the number of bonds and you divide it by the number of atoms. So here it says, illustrate the resonance structure and calculate the bond order for NO3 negative. So the first thing we have to do is draw the Lewis structure. And remember, step 1 is we count our electrons, our valence electrons. So nitrogen, we have 1 nitrogen with 5 valence electrons. Remember, we learned that up here. So 5 times 1 gives me 5 electrons. And we know that oxygen has 6 valence electrons from our previous example. And there's 3 of them. So that, excuse me, is 18. And then we have this little negative here. We can't ignore that. So that's an electron. We have 1 of those. So we have 24 electrons total. So I'm going to draw the structure. I'm going to put nitrogen in the middle with oxygen, oxygen, and oxygen. And so far I have 2, 4, 6 electrons that I've used, which means I need to use 18 more. So I'm just going to draw all these around here and then recount them. Hopefully they will add up to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Yes, so I used up all of them. And then I have 20, 22, 24. My oxygen, each oxygen has 2, 4, 6, 8 electrons around it, so that's good. But nitrogen has 2, 4, 6. That doesn't satisfy the octet rule. So what I'm going to have to do is I'm going to have to borrow an electron from any of these oxygens so that I have my octet. So now my nitrogen has a double bond. 1, 2, 3, 4. And this one has all those and this has 3. Okay, so that is one representation, but, and don't forget to add that negative. I'm going to take this, and move that down. Okay, so that's one representation, okay, and then I have to draw the other two. So now I'm going to put the double bond on this oxygen. Make sure you add your lone pairs. And then you got to draw the negative. And I've got one more to draw, and that one, the oxygen on top is going to have the double bond with the 2 lone pairs, and the others have lone pairs that have 6. Sorry, that one has 2 lone pairs, and this one has 3 lone pairs. Okay, so that's not the most beautiful, but you get the idea, and you would draw it like that, okay, with the negative. Now, if you were to draw it with the dashed lines like this, you can't really show the lone pairs. So I would stick with this format so that the AP reader can see that you're showing all the lone pairs on each of them, okay? And then it says calculate the bond order of the atoms. So what we're gonna do is we're gonna count the number of bonds. So we can just take any of these atoms, and I have 1, 2, 3, 4 bonds. So remember, bond order is the number of bonds divided by number of atoms. So I had 4 bonds, and then I have how many atoms? This is number of atoms attached, we should say. Number of atoms attached to the central atom, and that is 3. We have 3 oxygens, 1, 2, 3. Number of atoms attached to central. So let's just make sure you know that. So each of the bond lengths is actually 1.33. So again, it's a single bond is 1, a double bond is 2, and so this is a hybrid bond. So if you would imagine these were all dashed, that were 1.33 in length. So it's in between. Again, practice these. Practice makes perfect.